Okay, so we have this in this example, we have a main function. We have remember that we created different threads, and we want to effectively we want to effectively we create a threads, and then each thread runs this function, and in each thread we're going to convert one of the argument string that we pass to the uppercase. So we're going to convert it to uppercase, and then eventually return the argument here. Recall that when we call pthread create, we have this function pointer, the argument that we want to pass. We also initialize the thread ID because that's what pthread create returns. And there is an attribute argument which we skip, so it's null here. Also, okay, so also one thing to mention here, this struct that we pass is that something that we define ourselves. So it's up to you to define what struct you want to pass to a thread function. So in this particular example, we pass thread ID, then application defined thread number. So remember that the application defined thread number is something like a sequence number, that thread 1, thread 2, thread 3. Thread ID can be like a unique number. It can be just like a very large number which doesn't have anything to do to the sequential numbers. And then there is a part of the argument string, so that will have the command line arguments. So let me so then one thing to keep in mind that str do will duplicate the string. So what will str do? Let's check that on the man, right? So if you do man str do, it shows that it will duplicate the string, basically make a copy. By memory for the new string is obtained with malloc. So that's what it says. So it will allocate a new buffer with malloc. So therefore it has to be freed with free. So when we look at this example, we created strdup uargv, right? And then we return uargv as the return value from the pthread function. So here later, when we join a thread, remember joining a thread, we are going to wait until all threads are complete. So we do it one by one. So there is no guarantee that thread 1 will continue before thread 2, or will terminate before thread 2. But the way pthread join works, it will wait until the thread is completed, or if it's already done, it will immediately return. So we effectively going to wait for the first thread. If it's done, we're going to return. If then we're going to wait for the second thread, and so on. Most of the time we will just wait the very first iteration, but because all threads will pretty much simultaneously complete. So here you see that we pass the argument to res. Res is the void star. And this is exactly we call free for us, because this is a memory for the string that was allocated from malloc. We printed it here, and then we want to free this buffer, free res. So again, this is uargv, which was done by strdup, and that's the return value from thread start. So let's look how it actually runs. Yes.
What's t-info?
T-info. Yeah, so t-info is our defined structure. So remember that whatever we pass to the thread start or to any function that defines the thread is completely opaque data structure. We just pass void star pointer. That means we can pass any structure we want. So we defined our own structure, which is called thread info, which has these pre-fields.
Can't post just a thread.
Yes. So thread info, T info, you see it casts the argument to T info. And again, the return value, we treated the return value as char star, right? So this is str dupe, it returns char star. It's a string, but we return it as void star pointer. It's also possible. I mean, it's anything. I mean, it accepts one void star argument and returns void star argument. It's up to you to decide how you're going to use this void star. I mean, you can pack an integer in this void star if you want, just directly without pointing to any structure. Okay, let's try to actually execute it. So, and again, this example is in Canvas. I recommend that you download it and play with this. So let me compile pthread example.c. Take a look, and it's uploaded to Canvas. So it will generate a binary. Let me share the screen. So let me close this. Okay, this one. Okay. So now we're going to execute it. Let's specify 4 threads. So you can see that I have like 4 arguments that will mean that I'm going to create 4 threads. And return value is uppercase, A capital A capital B, and so on. So there is nothing unusual here. It creates two threads. In each thread converts to the uppercase, and then after 2 seconds, we were able to terminate. I mean, the thread terminates, and all threads pretty much terminate simultaneously, and we exit. So let's change it a little bit. Let's have pthread example, and let's have something that we can change here. For example, we can say if it's thread ID info thread number, not thread ID, but thread number is not 2, then maybe sleep 2 seconds. So let me replace this with this, and else sleep 10 seconds. So what do you expect will happen right now after I run it? So if its thread now number is 2, I will wait 10 seconds. So that will take 10 seconds to execute this thread. Otherwise, it's 2 seconds. So what do you expect will happen? Well, let's see. I mean, what will happen with join? So for thread 1, it will shoot immediately after 2 seconds complete, right? So not immediately, but after 2 seconds. But then it will get stuck on thread 2 for 8 more seconds. For 8 more or for 10? Well, because it's sleep 10 is instead of sleep 2, right? Oh. So 2 seconds already passed by that time, right? So we should say see 8 more seconds, and then finally thread 3 and thread 4 should immediately return. Two seconds pass, first thread is done. Oh, okay, then you see thread 2 completed after 8 more seconds, and all other threads immediately returned, because for them it was just 2 seconds. It was only the second thread that has to wait for 10 seconds. So you see the second thread was waiting 10 seconds. The first thread, the third thread, and the third thread and fourth thread, they were waiting for 2 seconds. So 3 threads completed after 2 seconds, and 1 thread was completed after 10 seconds. So now the first thread, after 2 seconds, you saw that message right away. Then the second thread, you waited for 8 more seconds, right? Because once you go to the second thread, it has to wait more. P-thread join for the first thread already succeeded, so it's done. But when we do the second iteration, we're waiting for the second thread. We have to wait for 8 more seconds now, because thread 2 has to complete. Okay, it's done. We finally print that message, and then immediately, why thread 3 and 4 immediately prints after this? Because by the time P-thread join comes, thread 3 and 4 are done long time ago already, right? So they're done after 2 seconds. So it just gathers the results for them, and that's it, right? So you can still call P-thread join even if the thread is already completed. So that's the way it works. So if the thread is completed, you can call P-thread join and get the result back, right? Otherwise, P-thread join will block and wait until the thread completes. So because we do it in a loop, we don't know whether thread 3 and thread 4 already done, because we were just doing it from sequential. Thread 1, thread 2, thread 3, thread 4. So we did thread 1, we found that it's done. So okay, we printed a message. Then we waited for thread 2, but we didn't even look at thread 3 and thread 4 yet. So we tried thread 2, we waited for 8 more seconds, and only after this we looked at thread 3 and thread 4. So let's try to change it a little bit. Let's put let's do in the opposite order. Let's have num threads -1 as a starting point, and then greater or equals than 0. And then tnum minus. So let's do p-thread join in the opposite order. So we'll start with the 4th thread, then 3rd thread, then 2nd thread, 1st thread. So what do you expect now? I'm sorry?
You'll finish in 2 seconds.
Thread 4 will finish right in 2 seconds. Then immediately we should see thread 3 message, because it's also 2 seconds. Then we'll wait for 8 more seconds. And then finally we should print thread 1 immediately after this. Okay, let's see. Okay, 2 threads done after 2 seconds, as we expected. Thread 4, thread 3. Okay, then final thread 1 after 8 more seconds, and then thread 2 after 8 more seconds, and then thread 1. And obviously thread 1 is done already because it was just taking 2 seconds. Yeah, so this is just to play with this example. Just download it from Canvas, compile the same way I did here, and just just try to modify this program, and I guess that's the best way to learn it. Okay, let's get started with today's. Any questions about this? Okay. Well, not. I mean, we are not. I mean, we haven't covered all material for Project 3 yet. So I guess, but yeah. So Project 3 will be about concurrency, but hopefully something more complicated than just p-threads, right? So yeah. Well, I guess the problem will be not so much about creating threads, but solving a synchronization problem, right? So yeah. Okay.
I would wait for the first thread. In this example, you're like checking on the first thread 1 thing. You want to check for like all the threads as that time as possible.
What do you mean? How do I check first?
So like you want to get the value of the first thread.
Yes.
How would you do that?
Only for the first one?
No, for all first one. Yeah.
The first one to finish. Okay. How do I determine? Well, I mean, with p-thread join, it's a little bit trickier. I guess what we can do what we can do, let's see in the documentation. There is so I guess there is p-spread join. It will not be possible to do it like this, but it's possible to do it with some other mechanisms, right? So for example, you can probably use some semaphores, which we'll talk about later, how you can actually synchronize that. So you can actually pretty much say that, okay, this thread is done processing this data, so as the result is already written, you can print it, so it's about to terminate in a second, like not in a second, in a moment, right? So that you can use semaphores to do that. And you can also have some sort of also non-blocking operation checking if that is done or not, right? So we will talk about this a little bit later. I guess with a regular pthread join, it's a blocking operation. You cannot really say it's either blocks or not blocks, right? So with pthread join, you cannot do it directly, but with some other mechanisms, you can do that. Does it answer your question? Yeah, I mean, not with pthread join. I mean, unless you can give me some example, but I don't think we can do that with pthread join, what you're trying to do. So it's basically by definition, it will have to be blocked. Yes. So yeah, not with pthread join. Okay. Anyway, good question. Yeah. So there is one thing that you can see. There is some additional functions. You can see pthread try join. So this is typically what is non-blocking operation. This is probably what you are looking for. Try to join with a terminated thread. So unlike join, it will not block. It will return, busy. Thread has not terminated at the time of the call, right? So unlike the pthread join. So there's a special version of that function. And you will find that in pthreads, there is a special version, like you have sem wait, sem try wait, and so on, right? So there's so-called try, there is prefix try whenever it's a blocking operation. So, and the same is for pthread join. Okay, any other questions? Okay. Okay, let's start today's lecture. So today we're going to talk about data races and race conditions. So just other things that you can explore on your own. This is pthread attribute in it, and so those attr that we have skipped. When we talked about pthread create, so you can take a look at this. Also, take a look at pthread cancel those additional functions. Again, not mandatory, but just take a look and explore it on your own. So let's look at one example, or like how we can actually use threads to maybe do some work. Let's say we want to increment the counter. And in this particular code, you can see that we have like a static volatile int counter. So volatility means that typically can be modified by multiple, by many, it's not modified by one entity, but potentially can change by other entities. But let's just keep that for a moment. Let's just assume that just basically disable some compile optimization. Let's look at the actual code in mythread. So there is mythread function, and in mythread function, we're going to iterate for 10 to the power 7 iterations. So you can see that 1e7, that's 10 to the power 7 iterations. And we're going to increment counter. So technically, what counter value we should expect? We should expect that it will increment by 10 to the power 7. And two threads are going to run. You can see that pthread creates two threads, so they will concurrently run, and then we'll do pthread join. Nothing really kind of weird here, so we'll wait for two threads to complete. And so we should, I guess, expect 2 multiplied by 10 to the power 7 as the result. So is that what's going to happen here, or we can have some issues here? What do you think? I'm going to increment the count in each thread. We just have 2 threads. Everything is fine. We do pthread join as expected. We'll wait for both threads to complete. We pretty much increment the counter for 10 to the power 7 iterations. So we should have 2 to the power 2 multiplied by 10 to the power 7. Okay, go ahead.
Maybe the threads will like preempt each other.
Yeah, so you think that the counter will be incorrect, right? So do you think the counter will be potentially higher or lower? Lower, right? Okay. Yeah, let's take a look. So when we run the program first time, we compile this program. You can actually try to copy and paste this code and compile it. You run it. You get the correct value first. 2 to the power 10, 10 to the power 7 multiplied by 2, right? So everything seems to be fine. You run exactly the same program second time without even recompiling it, and you get a completely different result. So now the result is lower. So why is it lower? So any idea why is it lower? Okay. So there are two one logical operation that we have counter plus 1 will actually consist of multiple assembly instructions, right? So and let's take a look what will happen if that is the case, right? Let me So what will happen is that yeah, so I guess let me write some x86 assembly. Even though in x86 the compiler can generate a better code, still that's going to be the case for, I guess, for RISC processors that you have going to have at least 3 instructions. And even for x86 it's still going to be an issue when we run multiple cores. So let me even if the compiler can fold it into one instruction. So we have, let's say we move the value, the like counter value to a register, let's call it EX, right? So EX will have counter, but do something like this. Then you will increment the value of EX of the register. And then we'll move the counter back to this variable. So that's just a comment, right? So that's just like in human readable form, right? So this is well, this is also human readable, but this is assembly instruction. Okay. Yeah. So you can see that this logically, what is appearing to be a logically one operation is actually going to have three instructions. So load instruction, then arithmetic operation, and then store. And that's going to be the case certainly on all RISC processors. I guess x86 is not RISC, at least externally. So the compiler can potentially fold it in a single instruction, still not guaranteed to be in a single instruction, because the compiler can easily generate this code as well. But you know, even if it's doing a single instruction, as I mentioned previously, it's still not correct. It can be still going to create issues on multiple cores. So what will happen here is that we will read the counter value here. And let's say two threads are going to read the same value simultaneously, or whatever, or almost simultaneously. For simplicity, you can assume that we even have like two cores, so two processors doing in parallel, right? One thread is running on one processor, another thread is running on a second processor. So they will read the same value of the counter, and later, like they will, let's say the value was 2. They will increment both, so both will get 3. So the first thread will increment 3 and the second thread will increment 3. So then they will write the result back, they will put 3. So instead of 4, we have 3. So we incremented the stale value. So what happened is that both threads had value 2, incremented it, assuming it's value 2. Now it becomes 3, and then one thread writes the result back, and then the other thread writes the result back. So we get 3 instead of 4. We should get 4 here because 2 threads incremented it. So we should get 2 plus 2 should be 4. So that is a problem. Moreover, even if it's just one core, just single processor system, what may happen is that we may get an interrupt here. Let's say timer interrupt here, and like maybe quantum from one thread is now expired. Now the second thread should run like we have round robin scheduling. So that means we have a stale value in the thread 1, and then after this we get an interrupt, we got preempted. Like the example, I think you mentioned preemption, right? Yeah, so we got preempted. So then another thread runs, also reads the counter value, increments it, so on, doing maybe like thousands of operations after us. Then we are going to be back in the original thread, going to increment the stale value, which is significantly diverged already, right? By 1, and write the result back. So we may even potentially write a smaller value than was already written there, right? So this is how bad it can get. So if we have preemption, because one thread can just read very stale value, increment it by 1, and write the result back. So this is also an issue. So there are multiple reasons why things can go wrong. You have multiple cores, you have interrupts, even if you just have one core. Also, CPUs can generate multiple instructions. Even if they generate a single instruction, maybe in x86, it can potentially fall to something like this, like counter. It's just a single instruction. Because it's still not going to work correctly on multiple cores, even if the compiler is able to optimize it. Because you have to, because internally it will still do multiple operations, and internally the bus will not be locked and potentially get stale value while executing this instruction internally, right? So inside the CPU. So you should still have some protection. In x86 there is a lock prefix that you specify. Unless you specify it here, it will be incorrect for multiple cores. So even if it's just single instruction, you don't have problems with interrupts, but you may still have problems with multiple cores. And certainly on the RISC processors, it's always going to be a problem, because on the RISC processors, this will at least take 3 instructions. So one issue we mentioned, interrupt. So just remember that this counter +1 doesn't really mean that it's going to be internally +1. So we may have 3 instructions. So anytime we can get an interrupt, and therefore, anything can happen, we can have a preemption. So again, just to reiterate, for RISC processors, you're gonna have a load instruction, add instruction, and store instruction. Even if it's not an assembly like this, internally in hardware, unless you specify like lock prefix or something like this, it can still execute it like this, because internally it can still be 3 different operations. So any questions about this? Okay.
I don't understand why it would work correctly directly after compilation.
Well, it's just you got lucky, so to say. And as I said, for x86, most likely, in this case, it's much higher probability that things will go wrong faster. With this thing, you may get luckier, right? So sometimes, if the code is well optimized, but you run multiple cores, maybe sometimes it didn't cause any issue, sometimes it caused an issue, depending on the exact timing. Especially if the instruction is folded like this, right? So like I run it on my computer, I have like 16 cores on my machine. It may maybe sometimes it's 2 threads are scheduled on 1 core also. That's also possible. Not very likely if I have spare resources, but who knows? Maybe other cores were busy with something else during that time. Or this didn't cause an issue in hardware because that's less likely to expose that problem. But still, the issue is there. Just because it works one time doesn't mean that it will always work correctly. And maybe with RISC processors, you will always get wrong value. I don't know, right? So that's more likely to be the case. Any other questions? So again, the reasons for that, there might be multiple reasons for that. Multiple cores, interrupts, how the specific behavior of the scheduler, maybe sometime you scheduled on 1 core, maybe sometime on different cores, how when you do the preemption and so on. So the specific condition can vary, but the problem is still there regardless. And the problem is going to exist regardless of the architecture or anything of that sort. So what we effectively have is so-called a data race. And a data race is when we have 2 memory accesses in a program where both first target the same memory address. Is it the case for counter? Yes, it's the case. We target the same memory address. Are performed concurrently by 2 threads. Is it the same for us? Yes, we have 2 threads running. Are not reads. They're not reads. They may be reading the counter value, but they're also modifying it. So they are not synchronization operations. Yeah, they are not just counter. And therefore, we can have a data race. So if all these conditions are true, we get a data race. Because the outcome may depend on the exact interleaving of threads. and how this happens. Like maybe schedule this thread first, and the other thread, maybe all threads are running on the same core, maybe running in different cores. You get a time interrupt. Sometimes you may get lucky, sometimes you didn't get lucky, and you get different results. So yeah, that's what a data race is. So now a race condition is a flaw. That's a flaw in a program that occurs when the time and ordering of events affect the program correctness. So now there is some subtle difference between a data race and a race condition. Even though they may look like very similar, there is some difference here. Let's discuss that difference. So data race may cause race conditions, but it's not necessarily. There may be race conditions for other reasons. Or sometimes you may have, like you may not have a race condition, but you still have a data race. So those are not mutually exclusive terms. Like, I mean, they may be different combinations. So let's look at one example, all right? Like when we have 4 different cases. Let's say we want to transfer some amount from one bank account to another bank account. Maybe like $20 from one account to another account. And you check the account from balance. You make sure that it's at least the amount that you want to transfer, because otherwise you want to reject the transaction right away. Okay, so we made sure that the amount is there. Then we're going to add the amounts to the account 2 and deduct that amount from account from. And then hopefully complete the operation. And we think maybe this looks like, from if you look at this looks fine, but is it actually fine? So what problems do we have here? So by the way, here we have both. Do we have data race here? So let's check. We are modifying the same. Let's look at the definition of data race. So we have the target the same memory location. Yes. So we have account 2, account from, and multiple. We can have multiple transactions in parallel. So their potential multiple threads are running that, and targeting the same memory address. They are not reads. Yeah, so we add or subtract, so they're not reads. Perform concurrently, yes. Not synchronization. Yeah, so clearly there is a data race because we update an account 2 and account from. So is there a race condition? Also yes. So, but the reasons why we have race conditions are actually different. There is a different race condition. There are different reasons. So can you mention at least some of these reasons? Like, can you give me some examples of race conditions? Okay.
I guess the balance of the account to where the account from could change in the time that we
Yes. So, and what will happen with the first check then?
it can become false or it can become true.
So, for example, I have $20 on my account from, right? So, and I want to transfer $20. So account from will only be updated as the very last step. But the first thing I do, I check the balance. So the balance, first time in the first thread, it's fine. I have $20 and I'm transferring $20. So it's still okay. So it's going to pass this check. However, it's also going to pass a check in the concurrent transaction, the second thread. So even though I'm, about to transfer this $20, so I have a second transaction to transfer maybe another $20. So that also succeeds. And then eventually account from becomes negative balance, right? So I have like minus $20. So I shouldn't have allowed that transaction to happen, but I allowed it to happen. That's one issue. And the fact that we have this check in front. But then there is another issue. So aside from this check, even if this check is fine, or like I solved this problem somehow, maybe I don't care that the account balance can get negative. We can still have the same issue as we discussed with the counter. You may have multiple threads, they may read the stale value of the account balance, you know, do some arithmetic operations simultaneously and write the account balance, whether it's to or from, doesn't matter too much, using the incorrect stale value. Does it make sense? So just the same way as we saw with the counter. So clearly there is a race condition and data race and race condition. So now let's look at the second example. So in this example, we will do atomic operation. So we will make sure that we don't have this problem like when one instruction is split into multiple pieces, like one logic operation is split into multiple instructions, like 3 instructions we had. So we will make sure that it's atomic. And atomic comes from atom, right? So initially atom was considered to be indivisible. Of course, that's not the case anymore, right? So we know, right? So, but atomic means potentially indivisible, right? So that means something that we cannot divide further. So, and in a sense, we do an operation atomically. That implies that we will, at least from the logical perspective, we will not have the spree instructions, right? So, or they will appear as a single operation. So how this is actually done, that can depend on architecture and depend on method that we are using. But let's just assume for a moment, so the value cannot diverge anymore, right? So that we do this operation, subtraction or addition, atomically means we cannot read the stale value. We always get the value that is correct, increment it, and then write it back. So we do it simultaneously, so to say, right? So without dividing into some multiple steps. Okay, we do this for account to balance, we do it for account from balance, we do that when we read the initial balance. So we don't have data race, right, per our definition, because we are not modifying the same, memory location non-atomically, right? So like we have a save modification of the same memory location. So it doesn't seem like we have a data race. But we still have a race condition. Why do we have a race condition? Well, I guess your example will still be true here. So we have a balance that we read, like $20. At least this if check can still erroneously succeed for the second thread. So because we read the stale value of the balance, we read the balance, we check it initially. Maybe we are in the process of modifying the balance for the from account, but that didn't happen yet. But we initiate the second transaction, which is going to deduct yet another $20, which we don't have that on that account anymore. So that example will still be true, even though other, I guess, examples will disappear, like when we non-atomically modify some variable. So those we can kind of dismiss from here, but we still have this check, and there is still a race condition. So the program is still not correct. So it allows the balance to go to a negative value, which is not what we expect. I guess you won't get $1 million accident on your account here, but you may easily get to a negative balance. So now this third case, let's say we do everything atomically, all this operation atomically, checks, account to balance, account from balance, we modify everything atomically. Of course, it cannot be done with a simple instruction, but let's say somehow we did it, right? So we will talk about this in a moment, right? How we can actually do that. So we did it atomically. So then there is no data race. Of course, there is no data race because everything is kind of done atomically. There is no race condition anymore. So we modify it consistently. If the balance is already, like if you took this $20, so the other transaction will not complete because this check is now done atomically with the update. So clearly this is, yeah, clearly this can solve the problem. We don't have data races, don't have race conditions. But now let's look at yet another example. I mean, is it possible to have a data race but no race condition? Yeah, that's also possible. Even though maybe you're less concerned about this, but still it's indicates some issue. So because I mean you're less concerned because the correctness is still there, right? So you can still get the same amount on the balance, but there is still technically a data race. So you will do this operations atomically, checks and updates of the balance, but maybe you will, before you do this, you will also set some flag to indicate activity on this account. So you'll set the flag to true. So it doesn't directly affect the correctness. So we still have, we still don't have any race condition here. But at the same time, clearly it is a data race, because if you look at the definition, we are modifying the shared memory location. Yes, activity. Yeah, so it's not done atomically, it's just done like regular memory write. So therefore there is a data race. But there is no race condition in this example. So this is just to kind of explain the subtle difference between a data race and a race condition, even though those are very often used interchangeably, but those are not exactly the same terms. So you may potentially have data race with race condition, you may have no data race with race condition, no race condition with data race, and no race condition with no data race. Well, hopefully you will be writing your programs like in the latter case, no data race condition and no data race. Yeah, so let's look at one example. So consider a shared linked list, something like maybe you did in the first project, and you want to return the first element. You want to, if the list is not empty, so that means the header of the list is not null. You want to return the first element and basically updated the head pointer to the second element in the list. So is there a data race here? So data race should be easy per our definition. So do we have a memory write to the same location, which can be done concurrently by two threads? Yes. So what is that? Is it, what line is that? Well, when we have h equals to h next, right? So we updating head. So that's the same memory location. We updating head. So we're going to write to the head location, and we're going to point to the next element. So there's clearly a data race here. I mean, maybe there is some other examples you can make here, but you know, there's clearly a data race here. So what about race condition? Is there a race condition here? So why yes or why no? Yes, that's the more important question. So you remove the first element. Let me draw an example. So if you remove the first element, let's say you have just one element in the list. And then you have head points to here. So is there any race condition if I have just one element?
Yeah, because if one thread updates head to next.
Yeah, so the first thread, so the first thing the first thread comes, yeah, it sees that head is not null, right? It's fine. So it's going to update head next. But the problem is that the second thread will also see that maybe it will read the stale value. It will say, okay, it's not null, so I can remove an element. So it will not return null, which it's supposed to return. The second thread is supposed to return null because we are already about to remove one element. So they're both going to update to the same point. So head is going to become null from both threads. And basically, both of them are going to return the same value. So they're both going to simultaneously remove the same element. It shouldn't happen because only one thread has to remove one element and the second thread should return null. Maybe it's the thread one returns null, that's fine, and the second thread returns the element. So the order is not predefined for concurrent executing threads, but certainly one of them should return an element, the other one should return null, but not like they're both return the same element. So it's like when you do malloc, you only call free once, you're not calling twice. So there is a race condition as well here, right? So there is both data race and race condition. And when we have a data race, very often we have a race condition. So this is why people sometimes choose it interchangeably, even though I have shown you examples where it's not the case. In the vast majority of examples, that's going to be the case. The moment you have data race, most likely you have some race condition as well. Okay, let's so let's see what we have learned so far. So even when we do concurrency on single process, we already have an issue because of interrupts. But clearly, with multiple processors, we have even more issues. So why do we even care about concurrency in the OS course? So on the multiprocessor system, multiple portions of the operating system will run on different cores concurrently. So and that means they will actually run in parallel. So that means it's not like semi-parallel, like or something like this, when the thread one just gets its own time slice, but they can really run in parallel. For example, thread one runs on the first processor, thread two runs on the second processor, and then we can have interrupts and traps in every of this processor. So, by the way, when I say processor in the OS context, that means any core. So it doesn't mean that there is a physical socket and physical processor. So if I have 8 cores on one processor, that's from the OS perspective is like 8 processors because there are 8 separate logical units that you can use to do the computations, right? So that means how exactly whether they're on the same chip or on different chips, that's completely orthogonal, right? So 8 cores, basically 8 processors from the OS perspective. Okay. So also on the single processor, we may have the same issue, just because we have an interrupt with switching from thread 1 to thread 3. So the same issue arises. An interrupt can happen in between some of these instructions, and which implement logically the same operation, but with multiple steps. So that clearly going to create an issue. So let's look at another example, producer-consumer problem. So that is the problem that we will also come back later, but let's look at one possible implementation. So, by the way, how many of you know what circular buffer or ring buffer is? Do you know what the ring buffer is? Okay, let me talk briefly. So in a circular buffer, what you have is, in fact, you have a collection of elements, and logically it's often shown like this. You have a like ring buffer, but it's like a ring, and this is your starting point. You write some data here, write some more data, write more data, and so on. Like you go to this direction. Then eventually you reach back the beginning, like you're gonna go back here. And by the time, maybe you already don't need this data, so you can potentially override it, some older data, and you know, like write a second, on the second round, you can write more data. So this is the buffer which can, you know, potentially recycle the same space over and over again. So of course, from the memory perspective, it's not a ring. From the memory perspective, it's a linear buffer. That's your starting point. And that's your ending point in the buffer. But what you do is that you have index. So you will have, so this is the buffer size. This is the buffer size. Like 14 buffer size, whatever it is, right? So then you have operation, maybe you're inserting first element here, second element here, you increment in I plus 1, plus 2, so on, right? Then you reach the end, you will have, and then after this, you kind of jump back here, right? So you'll have I plus 1 modular buffer size. That's your new I value, right? So that's exactly what we have in this code. So this is input parameter, so this is the producer. So producer is going to push some elements here, and the consumer is going to kind of try to consume some elements that was previously produced. So the producer and consumer, they have their individual pointers. So which points to the last produced elements or next produced elements or next consumed elements, depending on your convention, right? In this case, we have next consumed and next produced. So yeah, so here, what you're gonna do, what the producer is gonna do, a producer is gonna wait. If the buffer is full, I mean, I don't have any space to produce anymore, right? I cannot push any additional elements here. So this is while it will just do nothing, right? So it will just sit in this while. So by the way, the indentation is a little bit wrong. So like, so I guess buffering and this should be like at the same level as while loop, because while loop is just waiting. So then we have buffer in. We will see the, you know, we will put the next produced element. We will increment the input by 1 and module buffer size, and then we increment the number of elements in this buffer. So in the consumer side, we'll do the opposite. So if the buffer is empty, there is nothing to consume. So we'll just wait. So until we get some count non-zero, right? So then we read the next consume from the buffer out, from buffer out, and then do the out the same as for in. So it's just in different indices for producers and consumers, pretty much. And then we'll subtract count by 1. So what is the problem here? Is buffer, shared buffer an issue?
You could have an issue with the producer, right?
So, but is the buffer itself is an issue? I guess the buffer itself is probably not an issue because you have, even though it's the same buffer, there is no problem with the buffer itself because, you know, each time you're accessing different element in this buffer. So you're not technically accessing the same memory location. But the issue is again with the count. I mean, there's actually some more issues here in this code, because count can also be potentially be reordered, can be reordered by both the compiler, and which is worse, even if it's not reordered by the compiler, you disable this optimization, it can still be reordered by the hardware. So hardware sometimes is allowed to reorder some instructions. And count in this particular example can be, if you don't do it in special way, it can also reorder count. So, but I mean, even putting that aside, that this kind of things can get rewarded, and there is many things can get wrong here. Just looking at the simple example that we modify count plus plus and count minus minus. So that's a data race that we discussed previously, and that the data race clearly is going to cause race condition here, because you may potentially have inconsistent value of the counter. So you may read the stale value of the counter, update it like by 2 threads simultaneously. One is supposed to add, the other is supposed to subtract, but you get you get either subtract or add the value, right? So but not both, right? And then after these things will get wrong, so count can easily get more than buffer size, or count can get less than count can even get, I guess, less than 0 here. I mean, a lot of issues can happen, right? So at that point, so count can really go out of sync. And so that is the problem with the producer and consumer here. So even putting aside other issues, because this code has other issues as well. We cannot just, even if it's fixed count, it's still, the issue is still not fixed. At least on modern computers. Okay, so that's something to keep in mind. So why these data races are undesirable? Well, clearly one issue is that we can have correctness problems. And we don't want to end up with incorrect balance, especially if it's if you lose money, right? So you transfer something to your account and get even less money than you had before. Yeah, that clearly is bad, right? So you don't want to have that. So we want to have, and maybe sometimes it works fine, sometimes it's not working fine. You have to call technical support. I guess at that point you will say, okay, I'm not going to use this bank anymore. So there is definitely an issue. Performance issues. Also, there is a performance issue. You can have starvation. So that means when some thread is not able to make a progress, there is live lock, deadlock. So those conditions we're going to discuss. I guess some of them you can also argue that those are correctness problems, like especially deadlock. If you something like is hanging and stuck, or maybe live lock, the same issue, right? Something is hanging and stuck, like you made a transaction and you kind of ended in some limbo state. Maybe your account balance is not updated, but the system has crashed and no longer accessible. That's also not desirable, right? So that's even if it doesn't result in incorrect balance. I mean, clearly it's an issue. And another issue is that data races can be really dangerous because they may not always result in bugs. So I know that many of you in project one had this like garbled bytes or payload overlaps or something like this. But the good thing about those bugs that they at least can reproduce them. You can run the same test again, and it will print exactly the same message over and over again. So you at least can reproduce and then see what's going wrong and debug it. But what can be worse than this? Worse can be that sometimes things go fine and sometimes they are not fine. So maybe you compile the program one version, like release version, it's fine. You compile the debug version, all of a sudden bug disappears, everything works. I mean, maybe the release version is not fine, crashes, but you compile the bug version, trying to run it through GDB, see what the bug is, and the bug all of a sudden disappears. Or maybe you don't even compile a different version. Maybe you run the same program through GDB and the bug disappears. Why is that, right? So because it may like result in different timings, and timings can kind of hide this race conditions. So it's sometimes like like jokingly, it's kind of called Heisenbugs. Like I guess it's like an analogy from quantum physics when you make a measurement, like make an observation, and this wave function collapses, right? And the same thing here, right? You run it through GDB, make an observation where the bug is, and the bug disappears. There is no longer bug there. Yeah, so to say, right? So that means it's really bad, and yeah. So I guess just because you pass some tests doesn't really prove that there is no bugs in the program. You can pass all tests, but still the program has race conditions. And maybe it's going to be 1 in a million cases, 1 in a billion cases. I mean, I had one case when I had to look at the bug myself. I mean, there was some really rare bug. It was very hard to reproduce it. But I just looked at the code, found some, data race there, and I assumed that, if I fix it, the bug will disappear. Yeah, so I assume, I guess it did disappear because it was not reproduced after this. But it's something that was not easy to kind of prove or disprove, because you have a data race, most likely it caused this bug, but you don't know for sure. You just fix that and then hope for the best after this. Yeah. Also, one thing before we wrap up, I wanted to mention mutual exclusion. For mutual exclusion, obviously what we have described is not desirable. That we have this kind of code, which when you execute multiple threads, it's creating all this sort of issues. So sometimes you want to have certain parts of the program, and you want to make sure that only only one thread is running this part of the program. By the way, this is not the only solution to the problem. I mean, there's more complicated algorithms and more complicated solutions to concurrency issues, but one common solution is mutual exclusion. So only one thread is running this so-called critical section. So what is critical section? It's the place where you have these operations, where you update a counter, where you update the buffer, whatever we looked previously. So this is called critical section. So the idea is that only one thread will execute this critical section, and all other threads will wait until this first thread is done. So effectively, we will see our program as a collection of sections, like entry section just before the critical section. Then there is exit section after the critical section. And then maybe the remaining section where you don't care how many threads are running in parallel. Maybe they're doing this, some computations related to just this thread, and there is no need for any synchronization. So you can treat your program as a collection of the sections. So effectively, in the entry section, you will synchronize with other threads to ensure that mutual exclusive access. So you will make sure that only one thread is running. That means one thread will enter the critical section, other threads will wait. So then you have exit section where you will do cleanup when you'll hopefully allow another thread to enter, and so on. So and finally, the remainder section is when we are no longer interested in this resource. We may just do some other tasks which are not related to other threads. Yeah, so that's pretty much how we can do that. So let's talk about solutions for mutual exclusion next time. And also, I want to make an announcement. Just give me 1 second.